All right, then, thank you. Hey, everybody, welcome to the second day of my presentation. I have a new partner with you here. I don't know who all was here yesterday, but if you'd like, if you could put in the chat if you were here yesterday or if this is your first time, if you're new. Let's see if we have anybody that we have a chatty audience today. Yep. Okay, we have at least one person that was here yesterday. And if you were here yesterday, I'm gonna do some things. They're gonna look a little like I'm repeating a little bit of what we did yesterday, but I'm gonna do a lot more extra things that are gonna be lots of fun. And we have a new partner here that's going to be helping as well. And she is really excited to go here. So let's go ahead and get started then. First thing, just like yesterday, if you were here yesterday, don't answer to this, but I'd like everyone to vote in the comments on which item here I have or is radioactive. I have a smoke detector. I have some clay kitty litter, and then I have some no salt, which is a salt substitute, and a banana with some banana chips below. Let's see if anyone can guess which one of these is radioactive. Looks like people are a little less chatty today. Hold on. Okay, I got a banana. Having all of them. Okay. So I'm going to say right now, all of these things are radioactive. Let's see. I think I have another question I can ask about this. Oh, hold on. Actually, I'll just go ahead and show everybody or the radioactivity on this. I got a radiation detector, and this detector is called a radioisotope identification device. And it actually, not only can it tell you that there's radiation present, it can actually tell you what type of radiation you have. So it can tell you kind of what isotope. For those that don't know, an isotope is a single element that has a different number of neutrons. So it'll act the same as a element that's not radioactive when it comes to the chemistry, but it might be radioactive though. So let's go ahead. I'm going to show the smoke detector here. Let's see. Can everybody hear that? And that is radioactive. And this smoke detector has a isotope called americium-241 in it. And that is an alpha emitter as well as a gamma emitter. And I'll kind of talk about what the difference is between alpha and gamma a little bit later. But it uses the alpha in order to be able to detect smoke. Smoke will go into this hole here, and what it'll do is it'll block those alpha particles from reaching a detector, and it makes it to where the detector can tell you, hey, there's either smoke or there might be steam or something. So that's how a smoke detector works, and it is radioactive. Here you go, Mylan. Oh yeah, this is Mylan, by the way. Go ahead and set that down over there. Yep, go put it right by the filter over there. Yep, you can put it right on the ground. Thank you. All right, so let's go ahead now and show the kitty litter. See if I can get it to go off. Oh, there we go. Hopefully you can hear that. So kitty litter, like I mentioned, it's clay kitty litter, and it really likes to soak up anything, just like kitty litter should. It should be able to soak up liquids and your cat urine, and it also likes to hold on to radioactivity as well. Here you go. Oh, go ahead and get down first, and then I'll hand this to you. It's really heavy, huh? This is a full thing of kitty litter. Here you go. Hold on to that tight. There we go. and on the ground. There we go. I'm going to skip this for now. Now with the banana, I can go up to it and I'm not going to detect it with this detector. And that's because the radioactivity in it is fairly low, or it's too low to be able to be detected by a radiation detector like this. What you got to do with this is you got to kind of smash it up, put it into a little specialized container, and you put it on a specialized piece of equipment that has lead all the way around it to kind of block out all that background radiation and detect what's radioactive in this. And the primary thing that's radioactive in bananas is potassium. And I have banana chips because those are even more radioactive than bananas, because when you dry out your bananas, that's going to let go of a lot of your water, and it concentrates it and makes it even more radioactive. Oh, good. I have another person that was here last time. So I'm going to go quickly over this because it looks like we have a lot of people that were here last time. As I mentioned before, potato chips are also high in potassium, so they're also radioactive. Here you go. And I'm going to do a quick demonstration here of the no salt. You like that? And one of the things I'm going to be mentioning a little later on is how you can actually demonstrate this to your kids. If you're a teacher, you can demonstrate it to your students on how things are radioactive. Go ahead and pass me the tan detector, please, Mylan. Thank you. Strong, huh? Turn this on. There we go. And this is the sound of stuff that's radioactive. I got a little tiny source on here. But I'm going to show how this stuff that you add to your food has radioactivity in it. Here we go. You can hear that going off. Oh yeah, all sorts of that potassium in it. Only a small portion of potassium is radioactive. You like that? Oh, okay. And so those are some things that you can find right around your house that are radioactive. And I remember last time, one of the things that a lot of people were asking about is how can I find things that aren't radioactive, you know, for my kids, just because I want to kind of stay away from radiation. And I really hope that that wouldn't be kind of the takeaway from my presentation. My hope is that, 1 second here, let me wipe this away. What I'd like to communicate is the fact that we're always surrounded by radioactivity, and it's okay. It's not going to be a significant harm to your health, because we've been living around radiation, radioactivity for millions of years now, and it's something that our bodies know how to handle, and it knows how to repair itself from radioactivity. There's even some evidence out there that at low levels, it could be good for some of your cells. So let's go ahead. Give me 1 second here. And feel free to ask me any questions you have. If there's anything that came up yesterday that you had a question about, but you weren't able to get answered, please feel free to put that in the chat here. And I forgot to mention at the very beginning of this, my name is DJ, and I am a health physicist, and I deal with radiation. And my job is to protect the public and the environment from radiation and radioactivity, while at the same time being able to take advantage of the benefits we get from radiation and radioactivity. And so on today's presentation, I would like to go over more of the health effects of radiation. Oh, nope, I got it. Thank you. Thanks. And when it comes to when is radiation actually something that you should be really worried about? And I would like to say that in our normal everyday lives, there is very rare that we come upon an instance where radiation is going to be something that you need to be really worried about. Radiation is something that you should understand, but you shouldn't fear it. You should respect it. Now, with a lot of these items I'm going to show again today, uh, they are radioactive, but their levels of radioactivity are so low, I'll let my kids play with them. They're really not something that you should be concerned about, because there are all sorts of other hazards out there that are much more of a concern than the radioactivity that are in these items that I'm showing today. Go ahead, Mylan, and I'd like you to pass me the orange bowl. Okay, I have a question here. It says, what is the highest radiation of stuff that we eat? Great question. That right there, I should have brought it up with me. I forgot to bring it here. But let me name a few things that we might eat on the everyday basis that are radioactive. Like I showed here, you have your salt substitutes, you have your bananas, anything that's high in potassium. So your potatoes, especially fried potatoes and potato chips. Brazil nuts is a good one. It has both that potassium, the radioactive potassium, as well as small amounts of radium in it. Peanut butter, uh, really everything's radioactive. But when it comes to some of the most radioactive stuff that we consume all the time is really anything with high levels of potassium. So the bananas and potato chips would be what I would say. All right. Thank you. Yep. Okay. So as I mentioned yesterday, this is Fiestaware. It is made up of, or it has a glaze on it that has uranium, and it gives this really beautiful color. And I can actually take my detector up to it. And let me, while I'm bringing my detector to it, I'm going to kind of explain to you what this is. And so you can just see this goes crazy. Lots of, I just think that is just the coolest thing. Oh, that's probably, yeah, hurting your all ears too. And let me go ahead and put this on silent here. Oh, careful. Okay, so this detector here, this is called a pancake probe. This right here is the pancake probe on it. And this here is kind of the interface that uses this probe to give you a readout on how much radioactivity and how much radiation it's detecting. The pancake probe is made up of a Geiger-Muller tube in it. And the tube just happens to be more of a kind of a flat circle, like you took or a sphere and you kind of squished it down. So it's sort of an oblong sphere that's inside here. And right there, you can see there's a silvery color there. And if you look closely, there's kind of a grating on it. And that grating or that grate on it is kind of to protect that Mylar that silver is what's called a Mylar window. And it's a very, very thin piece of metal. And what that allows, having that window on it, allows you to detect certain radiation that if there was metal over this or even plastic over this, this detector would not be able to detect it, because there's certain types of radiation that can't pass through things as simple as a piece of paper or a piece of plastic. And I can actually demonstrate that here. I have a piece of plastic. This is actually the cover that goes on the detector. And I can kind of show here, it's hard to see in the camera, but let me reset that. All right. Turn on the meter again. You can see it's going off like crazy here. And let me go ahead and put this cover on it and see what happens. Oh, nope, still going off like crazy. So let me show a different item that maybe is not a little less hot. I'm going to show this one again. Oh, careful, careful. These are very fragile. Hold on. I got it. Thank you. I'm going to show the no salt again, even though I just cleaned up that spot. And I could show, hold on a second. All right, so I don't know if you can hear this very well, but like I said, see, it's going off pretty good there. But then now I'm going to put on this cover. Okay. And now it's still going off, but not as much. And the reason why, I can even explain it or show it on here, and it's not going to really go off at all, because there are what's called beta particles, and that's that particle radiation that I talked about a little earlier, is being blocked just by simple paper and plastic. There's also alpha radiation, which isn't present in here, that would also be blocked by this cover. Let me go ahead and, there we go. All right. And particle radiation, it's really a little different than your electromagnetic radiation. Hold on one second, okay? You like being in front of the camera? So are you embarrassed being in front of the camera? Particle radiation can sometimes be really easily blocked by things such as plastic and paper. So one of the things I really wanted to show is what's called a cloud chamber. And this is something that you could, if you wanted to show your kids or students radiation in our everyday lives, but you don't want to go buy a radiation detector, you can use what's called a cloud chamber. So let me go ahead and share my screen. Okay, give me 1 second. Hope everybody can see that. All right, so I have this here, a cloud chamber that I made. And this is really one of my favorite things. And it is a thing that looks kind of like a fish tank. And inside this fish tank is a isopropyl alcohol that has made a layer on the bottom of the fish tank, which you see it's kind of a black color here. And it creates just the right conditions to actually be able to see radiation. And these tracks that you're seeing coming off of it, you're actually seeing radiation in real time. And a lot of these tracks that are coming off of this thing here, I'll show you after I'm done sharing my screen. A lot of these tracks are alpha radiation. I was kind of trying to explain that a little bit before, but alpha radiation is one of those particle radiations that I talked about yesterday. And you can see these short tracks that are kind of shooting off of here. They're kind of these big tracks, and they're shooting off of this thing here. And this is called a thorium lantern mantle, and it contains thorium. And this right here is just, you're seeing the radiation shooting off, and it's interacting with that isopropyl alcohol supersaturated layer that I mentioned. And let me show another screen here. Make sure I don't have any questions coming up about this. Oh, make this bigger. Ah, yes, it is very neat. So let me pause that and get this one going. And I've mentioned this before many times during my presentation about how there's constantly radiation coming down on us every second of our lives, and it's also coming up from the ground. This right here is a really cool way to visualize radiation, or the cosmic radiation that comes from outer space down on top of us. You can see these short tracks in here, or the long tracks and some of the short tracks. Those are your muons and some of your particle radiation and protons that come from space down on top of us. And you're not even seeing a fraction of those particles that come down on here. These are just some of those that are coming down. And this is a really cool way you can demonstrate to kids and adults alike that we're constantly bombarded with these particles. And I could honestly watch this for hours and hours myself. Let's see if I have any questions on that. Oh, this is really neat. Yes. Um, yep. This is one of my favorite things. And I remember once when I was just getting into this job, somebody showed me this cloud chamber, and it just blew my mind that you could actually set up just the right conditions to where you could actually see radiation. And if this is something that you would like to do, you can easily go online and search radiation cloud chamber, and you can find instructions on how to make this. Maybe sometime on my YouTube channel, I'll make a kind of a tutorial on how I built this cloud chamber. But this is a cloud chamber that I actually built for my work, for my job, in order to demonstrate to some of the people we work with what radiation is. Yep, and I have somebody asking, what is my YouTube channel? So this is my YouTube channel here. Let's see, it is called The Rad Guy. So if you look up The Rad Guy on YouTube, you should be able to find this. Actually, I might be able to, or one of the people might be able to put a link in here. Let me put a link straight to this video, and you should be able to see it. Yep. Okay. Yeah, I'll just let somebody else put that a link in there. But I actually have some other videos on there that explains what is health physics. And the place that I'm probably most active is on TikTok. I'll do videos maybe once a day, once or twice a day. I'll do some TikTok videos that explain radiation kind of in our everyday lives and some other cool things that you can collect. So as I mentioned before, let me go ahead and stop sharing my screen. Let's see here. That thorium lantern mantle that I mentioned was inside that tank. I think my helper might have given up on me. That thorium lantern mantle, I have a bunch of them right here. And I don't know how familiar people are with lanterns anymore, but these are used on gas lanterns. They're just kind of a cloth, and they're that specific part that is glowing really bright. Let me go ahead and actually show what a gas lantern looks like. Oh, didn't mean to click on it. So here's your gas lantern. And the thorium lantern mantle is this part right here. When you light it, it glows a really bright white color, and it's the thorium itself that's glowing that really distinct bright white color. What's interesting is that some people have noticed that they're avid campers that when you get modern lantern mantles where they've discontinued the thorium in it, it actually glows more of a yellowish color, and it's not as bright as the white ones. So you get people that are very disappointed in the fact that modern ones just aren't as good as the new ones. Let's see if I have any questions. Thank you for putting that on there. And yep, the YouTube link. Awesome. Yes, and please follow me on TikTok. I hope to put a lot more educational videos about radiation on it. Currently, I mostly talk about my collection of uranium glass that I have, which for those who were not here yesterday, let me go ahead and show my uranium glass collection. These right here help protect from UV, and since I'm constantly using a UV flashlight, it's a good idea to protect from it. But yep, you can see here it glows this really bright color, and this right here is actually my funnest, or one of my favorite parts of my collection that's inside this glass. This is a sugar bowl. Here I have my uranium marbles. They just glow really bright. And I had a friend who gave me these marbles just maybe a month and a half ago. And ever since he gave me these marbles, it actually inspired me to start collecting. Yep, you can turn it off if you'd like. But it inspired me to start collecting these. He actually sent me these in the mail randomly, and it kind of spurred me into making a huge collection of uranium glass, depression glass. And I talk about it on my YouTube channel quite often. I actually give recommendations on if you'd like to find depression glass yourself or uranium glass yourself. I give some cool tips on how to do that. So let me go on to my next topic I'd like to talk about.
Wait, my hand's way when I in the camera.
All right.
Daddy?
So one of the things I didn't talk about yesterday that I like to talk about today. Yep.
When I in the camera, my hair turns gray.
Yeah, she says when her hair is in the camera, it turns gray. So one of the things I wanted to talk about is where does all of this radiation and radioactivity originate from? And this is actually a really cool thing. The uh, radiation or the radioactivity, those kind of naturally occurring things that are in your potassium, your thorium, all those kind of naturally occurring radionuclides or radioactivity comes from uh, a few different places. So first I'll mention your potassium. That's going to come from stars. So stars, it's your, hold on, your hydrogen and your helium fusing together. And eventually it's making all sorts of other elements. And one of them is going to be your potassium that it creates. And a certain small percentage of that potassium, those are lantern mantles. A small percentage of the potassium that stars make is going to be your radioactive potassium. For your thorium and uranium, they actually recently found in just the last few, nope, I don't need these anymore. In just the last few years, they've made this new discovery about where thorium and uranium came from. They originally thought that thorium and uranium came from supernovas. So when your very large stars kind of blow up, when that happens, they're able to create all sorts of heavier elements that a normal star wouldn't be able to produce. But then it was discovered in the last few years that a lot of these elements actually come from the colliding of neutron stars. So that's one of the things that we've been able to detect in recent history of neutron stars that are kind of circling around each other, and then they're going really, really, really fast, and they combine with each other, and they actually produce a lot of these really super heavy elements, or not super heavy, but very heavy elements, such as uranium and thorium. So that uranium and thorium that we have on Earth, it all comes from the colliding of neutron stars. And I just thought that was just really the coolest thing. Nope. I'm gonna put this away. Yep. Nope. The glasses are not radioactive. All right. Let me see if I have any questions here. Yep. So I have some people that are looking up my YouTube channel, and that's awesome. So that's where all of this radiation or all this radioactivity comes from. Remember, radioactivity is the stuff you can actually kind of hold on to. The radiation is coming off of the radioactivity. Now, it's not the only place where radiation is coming from. I kind of mentioned this a little bit earlier. A lot of the radiation is actually coming from space on us. And when you go higher and higher up in the atmosphere, you actually get a lot more radiation coming from space because you have less atmosphere to block it. And a lot of the radiation that's coming down on us, the cosmic radiation, it's coming from radiation being produced in our local sun, our local star. And some of it is coming from outside of our solar system, coming from the rest of the galaxy. Some of it comes from your supernova. Um, they're still kind of discovering where some of that radiation, where it primarily is coming from. But those are the places that it comes from. All right.
What? You done?
Nope, we're not done yet. So I'd like to see what other questions do you all have about radiation and radioactivity, or things you'd like to see again. Please put them in the chat and we can talk more about it. I decided to kind of speed through things a little more today just so that we'd have more time to talk about some of this other stuff and look at the cosmic radiation cloud chamber. So any questions that you all have, I would be happy to answer. If there aren't any questions, I think I will probably, I hope they're okay with this, but I'd like to end a little earlier. All right. Oh, sweet. Awesome. Okay. I have someone saying, asking if I can explain the difference between something that is radioactive versus contaminated. And that's a really good one. I love that. And what's interesting is I think I just kind of made my hands a little contaminated by handling this salt. So there's something that's radioactive and something that's contaminated. Something that's radioactive, let me give an example. This plate here, let me give something that's a little better. So this bowl here, you could say that this bowl is radioactive. And if I take a piece of cloth, or I take my hand and I wipe it on it, I'm able to take a detector like this one and show that, hey, I'm not detecting any radiation on it because this is radioactive, but not necessarily contaminated. Let's say I took a fork to this and tried to scrape it really, really, really hard and had some of maybe the glaze come off, the radioactive glaze come off, which would be really tough because this stuff is very strong. But let's say I did that, and then I wiped my hands on it and then used this detector, and I found, hey, it's picking up on some radiation. what it's picking up on is what's contamination. So contamination is something that you're usually able to remove from something, and then something that's radioactive, it's kind of fixed in the item as being radioactive. I hope that explained it. One of the things that people like to talk about is, or compare it to, is a fire, or the coals of a fire after the fire is kind of burned down. The coals themselves are kind of like the contamination. And then that heat you feel off of them is the radiation. I hope that helps. Let's see, I am getting all sorts of questions, and that is awesome. Give me 1 second to look up some of the, oh, I have some Q&A. I didn't realize I had that. Okay, I had somebody that asked, how could you see radiation from the alcohol? Let me go ahead and share my screen again.
Wait. I hear it on here.
Okay, I'm going to show this screen here. This is actually somebody else's YouTube channel, but I'd like to show you another instance of a cloud chamber and kind of explain about the alcohol. Okay. So here's someone else's cloud chamber that they made. They made a really great cloud chamber, and alcohol, or the isopropyl alcohol, you could see here, it's like dripping down and it evaporates. And then as it goes down towards this black plate on the bottom, that black plate is actually very, very cold. So what it does is it condenses down and gets and forms that kind of a super saturated layer, which, what does that mean? Even super saturated layer. A good way to kind of imagine it is like a plane flying through our atmosphere, and behind the plane, it leaves behind a trail because the water molecules in that, or in the atmosphere, aren't able to condense until the plane impacts the molecules. A very similar thing is happening with this isopropyl alcohol, the supersaturated layer of isopropyl alcohol. The radiation, it hits those molecules, and it causes it to condense behind it. So it produces very similar condensation trails, or contrails, as planes do. I hope that made sense. All right. And I think that, yep. So I hope that answered your question, Sam. Yep, you put it in the right place. Perfect. I have somebody saying that they like space radiation. And that's actually, if you were ever to get into my field, which is health physics, they're actually looking for people that are health physicists to get into the space radiation sector of health physics. So my field of expertise is very broad. You can get into the medical applications, industrial applications, research applications, and one of the new ones is your space radiation. So if you want to work for NASA or other companies that are kind of helping out when it comes to our space mission, they're actually looking for health physicists to help out with that. The program, I'm actually in a master's program where they are considering starting a small subsection of the program that does space radiation. And I think that's just the coolest thing. I think if I wasn't already almost done with my master's program, space radiation might be something that I would get into. All right. I have somebody asking, does paint have radiation? And I think the question might be more of, does it have more radiation than everything does? Like I mentioned, everything has a certain amount of radiation or radioactivity in it. Paint, especially modern paint, does not have radiation or radioactivity in it. Some of your older paints might have had lead in it, like your lead-based paints, not necessarily radioactive. Some of your older glazes were radioactive. The modern ones generally aren't, from my knowledge, radioactive. What other questions do we have here? Oh, so someone said, and radiation, since Hulk is gamma in Marvel, is that a good example of gamma? And I'm actually really glad that this question was brought up. And it's actually something that I'm trying to uh, I'm trying to kind of fight against, maybe not fight against, but uh, counter the common myths around radiation. And one of those myths are that if you're irradiated with radiation, you're going to become mutated. And that's actually not the way radiation works. You don't get irradiated by radiation and all of a sudden you become mutated. In fact, they've never had instances where radiation has caused people to develop mutations, or even their offspring after let's say somebody was irradiated with a really high level of radioactivity in some sort of incident, which those are very rare. uh, Even they've done studies of thousands and thousands of people who have received high doses, and none of their offsprings showed any effects. So there's no mutagenic effects that were carried on into the offspring. Those effects have only been seen in lab animals with high levels of radiation. So that's actually a very common myth, that radiation is just going to make you mutated or make your children mutated. We just don't have any scientific data that backs up that in humans. Um, we do, to try being or to be cautious, we assume maybe that there's some level, it's just very hard to detect. So the Hulk would have never, or that sort of situation would have never happened. If you get irradiated with too much gamma radiation, it would have to be a lot of gamma radiation, very rarely ever seen. That could lead to some health effects, immediate health effects, but that's a very rare instance. You're not going to get mutated from it. All right. I hope that answered that question. Queen Elizabeth had lead makeup. I have heard of lead in makeup before. So the lead itself is, it's really interesting because lead or comes from uranium, or some of it comes from uranium. As uranium decays away, it decays into a lot of different things until finally the most stable thing that it goes into is lead, and that's where it stops. Um, and so once it reaches the end of its decay chain, it's no longer going to be radioactive. So the lead that you're probably talking about in makeup um, probably doesn't have high levels of radioactivity. It's probably the more stable version of lead. Um, how does iodine 131 work in cancer treatment? This question really kind of spurs some interesting conversation. Uh, Iodine can cause, if you have a lot of iodine, like let's say you had a nuclear explosion that happened, like a nuclear bomb explosion that's produced a lot of iodine, and a large population of people were exposed to this iodine by inhaling it. It could cause issues with your thyroid, and it could cause thyroid cancer. And that's with, again, a lot of iodine. Uh, what's interesting about that is that one of the treatments for thyroid cancer is iodine. So it can cause the cancer, but then it can also be used to treat the cancer and cure the individual. So iodine, I should have mentioned, it likes to go straight to the thyroid because your thyroid really picks up on lots of iodine, and that's why it both can cause cancer in the thyroid, and it can be used to treat cancer in the thyroid because your thyroid will soak up all of that iodine. I hope that helps. Okay. I I am glad to hear that you're having fun learning. I could talk for hours about radiation, radioactivity, and even nuclear power. That was actually my undergrad, was nuclear engineering technology. So if you are around too much radiation, can it hurt you? And yes, if it is very high levels of radiation, it can hurt you. That's one of the things I kind of wanted to focus on today. That the again, on those health effects of radiation, being exposed to high levels either in a very short time, like let's say it was just a big blast of radiation, um, or if it was exposed to kind of still a high level of radiation for a long period of time, those can cause some other health effects. So yes, it can hurt you, but again, that is very high levels of radiation that are very unlikely for the general public to be able to see. I have somebody that said, yes, it can hurt you. Yep. Okay. And what does it hurt? So if it is like a lot of radiation in a very short period of time, it would cause acute radiation syndrome or acute radiation sickness. And though that's not fun. It gives you first kind of some cold symptoms, and then it depends on how much radiation you get on how severe those symptoms are. Um, but a high enough radiation could eventually lead to death. But again, you could actually probably count the number of people who have died from that on two hands. So it's not a extreme amount of those people that have had that high dose of radiation. And then if it is a lot of radiation, but over a long period of time, so maybe it didn't reach high enough amount of radiation to cause the immediate sickness, but it was just high enough, and over a longer period of time, it could lead to a greater chance of getting cancer. And the thing is, it's very hard to tell that, let's say you did maybe down the road get cancer. It's hard to say that, oh, it came from this um, dose of radiation that I got at this period of time. You can't, it's very hard to draw those links. And the reason why is because us in the general public, we it's very common that we are all going, or at least 50% of us are going to get cancer, and that's just from being human, not not necessarily at all from radiation. Radiation itself is actually a very weak carcinogen. Um, but the only way that we know that radiation can lead to cancer if you have kind of a large amount of them is by taking a population that maybe received a large amount of dose, such as the Japanese survivors of the Hiroshima and Nagasaki bombings. We've done studies of them that have lasted for many years, and we could tell that, oh, this certain population that got received this dose, they experienced a certain percentage extra of certain cancers. But you couldn't say that any of those cancers specifically were linked directly to the exposure they got during the bombings, because um, no matter what, a very large percentage of them are going to get cancer anyways without even without a radiation dose. And what most people don't know is that those people that did uh, uh, get cancer from those bombings, there's only a fairly small increase of incidence of cancer um, that came from their exposure, and those were very high levels of radiation exposure. Yet the number of people that received cancer from it wasn't actually that high, and that's because, like I mentioned, radiation is a very weak carcinogen. There's many other things that we consume actually on the daily basis, such as alcohol, that is much more carcinogenic than radiation. So uh, the radiation in kind of our everyday lives, not something that we really do need to be too concerned about. Let's see here. Okay, yeah, someone read a book about a person who got sick from radiation from the bomb, and they got leukemia. So what's interesting, like it's really hard to say that I got leukemia. It must have came from this instance. Um, you could say, though, in a large population, we saw a 2 or 3% increase in leukemia over the normal amount of leukemia that we should have expected. It's hard to say specifically that it came from a certain exposure of radiation. And I think that, oh, looks like we're running out of time here. Oh, we are. I would love to keep talking about this. I'm so sorry. Maybe tomorrow, go ahead and bring more questions. Um, and maybe we can start talking about this more. Yeah, sorry, see some smile or some frowny faces because we're running out of time. Okay, you'll be there. I'll make sure. I'll probably skip some of the showing the real basic stuff, and we can really kind of get into some stuff. So thank you so much. I really look forward to seeing you all